And so this again is a whole course. All these little topics seem to be whole courses, but what I want to do is talk a little bit about probability, because that is how we get from quantum mechanics and the energy level diagram that you're familiar with. You know, we did the energy level diagrams for all kinds of things, whether it's rotational or vibrational spectroscopy, and we're going to throw a mole of atoms or molecules in there and populate those energy levels with the Boltzmann distribution and so on, and then we'll get the thermodynamic properties that come out. But let's first just sort of refresh our understanding or learn a little bit about the basics of probability. So there's several types of theories of probability. There's the logical theory of probability. And when you think about logic, you're thinking about rational degrees of belief given some evidence. And so that evidence, we like for that evidence as scientists to be empirical, something you can go in the lab and measure. And so the empirical part of this is a mathematical description of measurable properties, and it's a foundation of a logical probability theory. Now, this is all background information, so it's not like you have to scramble to get everything, you know, recorded word for word. What I'm trying to do is just give you a background of the random population of energy levels and talk about thinking in terms of what's more probable and what's less probable. Okay. And then there's also the subjective theory of probability. I just put this in there to round it out, because we have logical probabilities and empirical probabilities, and then we have the subjective probabilities. But the subjective is important because that's really how you make decisions. You are an individual mind, and your mind weighs the evidence, weighs your emotions, weighs all of these inputs, and makes decisions. Okay, and in science, we are a part of it. We are making the measurements. And in quantum mechanics, we actually cause some funky things to happen in terms of collapse of wave functions and so on. So the observer is a part of the whole process. So our subjective inputs in terms of probability get to play a role, and we'll see how that works. So in this case, the probability of an event is an individual degree of belief. Notice individual is the key there. So it's what we call mind dependent. And so this is a nice, just in general, something you really need to think carefully about. That is the difference between objective and subjective. So one way to break that, objective versus subjective, is to think about if it's mind dependent, it's subjective. And if it's mind independent, it's objective. So in this case, subjective, it's an individual degree of belief. So that's the mind is involved. And so that's a subjective thing. Whereas, the position of this cup on the table is objective. There's no mind involved there. Now we can take measurements, we can get multiple minds in here. We should get the same answer if we're using the same procedure and the same tool as to the location of that cup. So its position is a subjective, is an objective fact, and we can bring our subjective minds, all different minds, in to make that measurement, but we should all get the same result. So that means its position is mind independent. So it's an objective fact. And you can imagine now in today's world with news and fake news and real news and whatever kinds of things, these questions, objective versus subjective, are really important. We can't get into that, but it's nice to think about. Okay. Now can be a dramatic difference between logical theory of probability and this subjective, because this is how we make decisions, this subjective idea. So let's look at how we make decisions. So the animations may be a little out of order because of Top Hat. When Top Hat converts the PowerPoints over, they don't necessarily come out in the correct order. So we have a subjective, we're going to make a decision. Again, I call this a little philosophy minute. We can have an uninformed opinion, and we can just go with our gut and make a decision, okay? We're still using probability because we have some evaluation in our mind as to the way we want this to go, and so we make our uninformed opinion. We can become informed, okay? Let's go over here. We can make some measurements, okay? And with those measurements, we can come up with evidence-based data, and we can say, yeah, let's use our rational mind, use logic, inference, and so on based on this data and make a decision. And I call that the green path because it's going to be one that is less mind dependent, right? If I look at the data and make a decision, and you look at the data and make the decision, and we have the same goal, we'll probably make the same decision. So in that case, that decision is objective, not subjective. We do this quickly, and sometimes we can skip that measurement system step and not actually have the data, but we can still use our rational thinking as to what we think the data would produce. Notice it's yellow. It's still a good way to think about it because you're using rationality. You're using what you think the world is like, and so you're still using a rational decision-making process. You just may not have the correct data, or you may assume some things about the data. But you're not just making an uninformed guess or an emotional decision. Now, you can go through this path many, many times, and eventually you form an expert or an informed opinion. And as long as the data hasn't changed, you'll be correct. But if the data changes, you'll be incorrect. And so that's why it's yellow again. So we talk about the experts a lot in the news right now, the experts. We just need to make sure that that expert is connected to the data and that they're committed to changing their opinions, their expert informed opinions, based upon the empirical measurements and the data that they have. And so when the data stops being collected, our experts get entrenched in their particular direction, then the green light starts turning yellow, right? And so this is just a nice little chart on how we make decisions based upon logic, inference, and emotions. Okay. And so let's just, let's see, okay. So looking at the numerical side of things, logical probability, this P of E, that's that P value. And we talk about that in our ANOVA outputs and so on. We have these P values. And so that P stands for probability. So this is the probability of event E happening. And that's the number of favorable events divided by the total number of events possible. So there's our equation. Our probability of a particular event is the number of those events over the total number. Now, this poses a problem in that how can we ever know the denominator? You have to know all of the possible events. Okay. Now, that's why we, a lot of times, as P chemists and just scientists, we reduce the number of events to 2. We just reduce it to a 2-level system. I've got heads or tails, that kind of thing. And so but we may not be correct. There may be a third option. And so sometimes we mess up. Now, each event must be equiprobable. We'll run into this a little bit in our energy level diagrams, and we'll have some questions about that. So equiprobable events can be hard to prove. It's hard to prove that heads and tails are equiprobable. So a lot of times we have to do a random trial. We just have to flip 1,000 times and see if it matches a Gaussian distribution. If it doesn't match a Gaussian distribution, we can come up with the probability using a Gaussian distribution that we would have this many tails. And that's that p-value again. So we would assume if it's normal, what's the probability of having 17 tails in a row? And if that probability is much, much lower than what we're comfortable with, then we could say, well, it may not be equiprobable. There must be something that favors tails in this situation. Okay. And then we have this, because we can't prove that the events are equiprobable, we set up the barrier to say, well, we're going to call them equiprobable unless there's a reason to not call them equiprobable. So that's called the principle of insufficient reason. It says the probabilities of 2 events will be equal unless if there is insufficient reason to believe the probabilities will be different. In other words, we're going to say this is a normal distribution, and then we're going to test the specific case to see if our assumption was wrong. So we assume it's normal, and then we do the p-value to see if it matches the distribution that we're assuming. And that's the principle of insufficient reason. So sometimes it sets too many probabilities to be equal. Not everything is equiprobable. Okay, but we have to figure out how to determine when those cases are. So we assume a normal distribution, and then we test the special cases. So let's look at one of our first questions this morning. Now, when we were doing this in the fall, we used the Boltzmann distribution. to populate our energy levels. We're going to get into that in a great deal in this first part of the course. It favors low energy levels at low temperatures. But other than that, is there anything special about the ground state? So in an energy level diagrams, we have excited states and we have a ground state. Is there anything special from a probabilistic standpoint of the ground state? And I know you probably are guessing, but that's okay. I wanted you to come in and so give me your best guess. Okay. So everybody thinks that the ground state is special. So let's discuss what is special about the ground state. So we have 15 out of 19 said the ground state special. So go ahead. Someone that thinks the ground state special, give me a couple of reasons why you answered that way. So,
your lowest energy level?
It's your lowest energy level. So it's in that case, it's unique. Okay. Okay, that's fine. We're good. Okay.
Doesn't it take the highest amount of energy to go from the ground state to another state?
No, because they could be non-equally spaced. So it could be a real small gap to the first and then a bigger gap to the second and so on. You're right that it's the lowest energy, so that makes it special. And that's what the Boltzmann distribution favors that. But in terms of atoms or molecules being in that ground state, there's nothing special about it. It's just another state of the molecule. Okay. So the Boltzmann distribution is what makes it highly probable at low temperatures. Okay. But if we increase the temperature, the Boltzmann factors become equal for all of the states. And then there's no specialness to the ground state at all. It's just another state like any other. So, if we come in here, like if you play musical chairs, you got a circle of chairs, you're going to pick the first chair that's available, okay, when the music stops, right? And that's what atoms are doing too. And then it's the Boltzmann distribution that will thermally equilibrate that situation. Okay. So I just wanted to really emphasize with this question that there's nothing special about the ground state. I mean, you can list some unique characteristics, like it's the lowest energy level and so on, but that doesn't give it any statistical importance. So we're talking about from a statistical standpoint, there's nothing special about the ground state. Okay, so that's an important concept. Now for empirical probabilities, whenever we're doing measurements, of course, we don't study a single event. We're studying thousands upon thousands of events, and we're getting an average. And so empirically observed sequences are always finite. So we can't ever get the full distribution. We can always get a sample. Even we can call it a population, but we're not really mapping out the whole perfect distribution because we don't measure all of the possible events. But trends do emerge as the sample size increases. And these measurements typically fall within one of these distribution functions. We're going to be talking about the Gaussian distribution function because that's the normal distribution function, almost always. But when we do measurements where it's like counts per minute, like in the radiation case, anything where it's got a per in there, like counts per minute or deaths per 100,000 or something like that, those follow the Poisson distribution. So that's an example of a different distribution. The Poisson distribution is any of those ratios measurements. But we're really going to just focus on the Gaussian the whole time. Okay. And then it's interesting, we try to say that the distribution is random, but we really don't have a way to measure that. We assume it's random, and then we look to the probability of our real distribution and see if that probability is acceptable or not. Okay. So let's look at some of there's first, second, and third laws and so on of probability. So what's the first law of probability? Probabilities cannot be less than 0 or greater than 1. So that's the full range of probabilities. We typically call it 100, percents. We multiply this by 100%. So we have, 100% chance or 50% chance, but it's, the decimal equivalent is 0 to 1. So really, really low probabilities, are still greater than 0. Do you ever see that Jim Carrey clip? I don't remember seeing the movie, but the girl says if there were what does she say? If there's something, do you remember what I'm talking about?
Yeah, I think she's like, oh, I wouldn't even if you're the last man on the world. He's like, so there's still a chance.
That's right. If you're the last person on Earth, I wouldn't. So there's 7 billion people on Earth, and he's like, so there's a chance. Right? The probability is not 0, and that's the funny thing. He's got a 1 in 7 billion chance, so he's holding on to that 10 to the ninth, 1 in 10 to the ninth. And so a lot of times you'll hear probabilities written that way. Let me do this. So we write them as a fraction a lot of times. So let me get this small one here. And so we'll say that the probability, let's see, come on. Why won't it write? Yeah, okay. They say 1 part. Golly, this pen pad is not as good as PowerPoint. That's for sure. All right. 1 part, that's an R, in 10 to the 9th. Come on. So do you understand that language? The probability is 1 part in 10 to the 9th. That's the same as writing 1 over 10 to the 9th. Okay. And so you hear this in discussions all the time of probabilities. So they'll say 1 part in 10 to the 9th, or like the probability of the current entropy in the universe is like 1 part in 10 to the 120th. Okay, so it's very improbable. Okay, so the probability of a sure event is 1, impossibility is 0, and so that's what we do. So now we have the second law where we start to combine probabilities, where we have this or that or that or that. So the OR function, how do we deal with the OR function? We have 2 events. We're going to draw an ace or a 2. You're counting cards for blackjack. What are you going to get? And so the probability of either of 2 mutually exclusive events occurring is equal to the sum of their individual probabilities. Okay. So events that are mutually exclusive, if the occurrence of any one event means that none of the others can occur. Okay. So if we have the probability of E1 or E2, that's just the sum of the individual probabilities. So that's how you handle the OR function. And so let's think about this in terms of chemistry. What's the probability of having a carbon-13 methane molecule? Okay. So this one doesn't use the OR function just yet, but it's setting us up for the next question. Okay, so we have, do you remember what the probability of getting a C13 is? If you've got 100 carbon atoms in a bag and you reach in and pull them out, what's the probability of getting a C13? Go back to organic.
25%.
25%. Okay, let's look at the periodic table. Okay, so carbon, the periodic table's masses are based on a carbon-12 system. So carbon-12 is exactly 12. Okay, and carbon-13 for our purposes is 13. Okay, AMU. So what's the average mass of carbon up there?
12.01.
12.01. So it's higher than 12. Okay, because of carbon-13. And it's 0.01 higher. What do you think it is? That's the probability of the carbon-13, is that extra 0.01. Okay, so it's 1%. So 1% of natural carbon is carbon-13. And you should have gotten that from your NMR, like when we're doing carbon-13 NMR. So you should remember, okay, 1%. So that's our baseline knowledge for the next problem. So the probability of getting a carbon-13, if I've got 100 carbon atoms in a bag and I reach in and pull them, 99 times out of 100, I'm going to get a carbon-12. But there may be a chance that I get a carbon-13. If I'm making my methane molecule, I reach in nature's bag and pull out the atoms and put them with the hydrogens, and what do you know? I've got a carbon-13. It's one chance out of 100 that I would get that. So let's do our next question. What's the probability of benzene having a single carbon-13 anywhere in its structure? And this uses that Boolean OR function, right? There's 6 positions. So it could be in the first position, or the second, or the third, or the fourth, or the fifth, or the sixth. So that's our next question. Let's see. So what is the probability of finding a carbon-13 atom anywhere on the benzene ring? Y'all can talk. This isn't a test. Two more people. Well, you know your answer has to be between 0 and 1. Okay. What's that? Yeah, percent. Okay, 0 and 100. Yes, very good. Thank you. Yeah, they're like, sorry. Yeah. Yeah, that's right. Okay, good. All right, so let's see what we've got. This is great because it'll give us a distribution of answers. All right. Okay, so what do we, let's see. Yeah, all right. So that's good. Most answers were 6, and that's correct. Okay. So how do we get 6? There are 6 positions, and that's the OR function. So each one is 1%. So there's a 1% chance of it being in position 1 or 2. So there's another percent, or 3, another percent, or 4. Since we have 6 chairs, and we're pulling these out, there's 6 times the chance that I would have one benzene or carbon-13 in one of those chairs. Now, it's not exactly 6% because we have other options. Remember, the denominator for probabilities is all possible events, and we could have 2 carbon-13s. It's not very probable, but it does reduce this percentage a slight amount. But what we say is, at a first approximation, this is correct. Okay, so you'll hear those words to say, look, if we're just not talking about double carbon-13s, we're just dealing with 1 carbon-13 and we have 6 positions, each one of those is 1%. So the OR function, we don't care which position it's in, adds those probabilities. And if you look at the mass spec of benzene, you'll see the 2 peaks. The benzene carbon-12 peak and the carbon-13 peak will be 6% of that, roughly. And this is how we get isotopic patterns in our mass spec, is using these probabilities. And there'll be a tiny little peak next to that one that has 2 carbon-13s in it, but it would be really small. Now we'll go to the next section. Okay, so good job on 6. Now the second corollary to the second law, the sum of all the probabilities of individual events are mutually exclusive and collectively exhaustive. equal to 1. So that means all of them. So if you sum all events, they equal to 1. So all your probabilities sum to 1. Because again, it's this or that or that or that. You add them all together, you get 1. This is called normalization. And we did that in a functional case with our probability distribution in the quantum mechanics section, where we said the wave function squared is our probability distribution. If you sum from all over all space, that should equal 1. So we forced it to equal 1, and we forced it to equal 1 with a normalization constant. Okay, what about the AND, the Boolean AND operator? Often the probability of an event depends upon the occurrence of some other event. This is known as a joint event. Like if you wanted to get an ace of spades. So it's both things have happened. You've drawn an ace and you've drawn a spade. So this is how you would say that. What are the odds of an ace given spades is selected? So you pull a spade out. What is the probability of it being an ace? These are multiplied. So you have the probability of an ace and a probability of a spade. Those are multiplied by each other. There are 4 aces in the deck. There are 13 spades in the deck. And there's 52 cards in the deck. So you know all of the parameters. And so the probability of getting an ace is 4 out of 52. A spade is 13 out of 52. You multiply those together and you get 1 out of 52. Now you could also have just said there's only 1 ace of spades in the deck. But you could do this with face cards and so on and come up with your probabilities. Now, this will allow us to calculate the probability of getting a C13 benzene where all 6 are C13s. So what would that probability be? I don't have that problem in here as a top hat, but let's just discuss our way through it. So notice how this is an AND event now, because we have a carbon 13 in position 1 and 2 and 3 and 4 and 5 and 6. So what do we do with that 0.01 or 10 to the minus 2 probability? So the carbon 13 being in the first position is 10 to the minus 2. And now we have one in the second position, given there's one in the first position. So these are AND events. So it's another 10 to the minus 2. So they're multiplied according to this. And so now it's 10 to the minus 4. And then the next one would be another 10 to the minus 2. So we're at 10 to the minus 6. Okay, 10 to the minus 8, 10 to the minus 10, 10 to the minus 12. So it would be one chance in 10 to the 12th that we would get a fully substituted benzene with carbon 13s. Okay, but there's a chance, right? Jim Carrey. And in fact, 1 in 10 to the 12th is not that unusual when you have a mole of molecules. You have 10 to the 24th or 10 to the 23rd things. It's likely that there's at least 1 or 2 benzenes that are fully substituted with carbon 13s. Really heavy benzene. Okay, but it's not very likely. There's a chance. Now we can take this, we're dealing with benzene with 6 positions on the ring, but you can imagine that things get more complex as you have more and more events. And sometimes those events can be described with functions. And so we have this situation where we have characteristic functions that describe our probabilities. And so we can take those probabilities and multiply them by items of interest, right? And so that's what we talk about, expectation values. And so here we have the value function. That's the thing we're really interested in. And in most cases, it's energy, but it could be volume. It could be some other property that we're interested in. But in this case, it's energy. And then we have some function of favorable events divided by the sum of all of these possible functions. And so that's the probability function. And so we'll show an example of this because this is kind of a confusing equation. So here, let's play a dart game. Let's go to the fair. We see a dartboard. We're pretty confident that we can get the dart on the board every time. But when we get it on the board, we're really not that good to know that there's a higher probability of being in the red or the blue or the green. So we're going to take a very conservative estimate of these probabilities and say that there's 100% chance that we'll get it inside the bigger ring. But inside there, we're going to just go by the area, right? So the smallest area would have the lowest probability, the middle area would have next highest probability, and then the green, the largest area would have the largest probability. So we'll just go by area units. So what are the areas of a circle? Well, the area, is pi r squared. And we can look at the radius here. The red has a radius of 1r. Blue is twice that radius, and green is 3 times that radius. So we could come up with our area equations, and you see those over here. Hopefully that's straightforward to you. So the area of the red is pi r squared. The area of the blue, again, we have twice that radius, and so this 2 squared comes out. That's a 4 pi r squared minus the red area. So we subtract that red area from the blue, and we end up with 3 times the area of the red. And then the green is 3 times the radius, so when you square that 3, it becomes a 9. So this is the area of the outer part of the green, and we subtract the area of the blue, so we just get that band of green, and so that's 5 times the area of the red. And so our probability of being in the red is that, again, just the ratio of the areas. So we have the area of the red divided by all of the areas. A red, a blue, a green. That's why I wrote blue and green in terms of red. So we have 3 and 5. If you add all those up, we got 9 times the area of the red. Look at that. The areas of the red cancel, and we have a 1/9 probability of hitting that red dot. So this is our probability function that we're calculating. We haven't gotten to our value function yet. We're just calculating the probabilities. And so this says if I throw my darts, 10 times, one of them is likely to hit the red. Okay. Then the blue, so we take this area of the blue, which is 3 times the area of the red. We put that in here and divide by all of the possibilities, which is 9 times the area of the red, and we end up with 3/9. And then up here we see that the green is 5 times the area of the red, and the total is 9. So we end up with 5/9. So these are our 3 probabilities. And that's our probability function. But we're not interested in probability. We're interested in money, right? We're at the fair. We want to win some coins. Okay, so the carnival barker says, yeah, if you hit the red square or red circle, you get $5. And it's only $1.50 to throw a dart. Hey, that sounds like pretty good money. Okay, $2 for the blue, but 0 for the green. Okay, and so we take the probability function and we multiply by the value function to get the expectation value. So that's what we're talking about. The expectation value is that on average what we're going to get out of this distribution. So notice how I just want in your mind to think of the 2 parts here. You have a probability function, and then you have the expectation value, the interest, the thing that you're interested in. In this case, it's money. Okay, so we take our value functions, $5 times its probability of 1/9, $2 times its probability, and $0 times its probability. Add those together, and it's $1.22. So now let's think in terms of the carnival game. He brings in $1.50 over and over again, and on average, he pays out $1.22. So it's an advantage to the carnival of just a few cents, but over time, that's enough to pay his wage and his lunch and whatever else. Okay. So that's again, I just want you to get in your mind that it doesn't matter what the value function is. You come up with the probability function, and you can multiply that by any property. It could be volume, it could be energy, it could be any property that we're interested in. So once you have the probability function in, then you can, if you have values associated with those various states, then you can put the value function in. So let's do this with energy. What if the green was 0 joules, the blue was 2 joules, and the red was 5 joules? Okay, the expected energy of this system at equilibrium would be 1.22 joules. So just sort of emphasize, this is, if we throw a mole of molecules at this system and it had those energies for the red, the blue, and the green, then we would have, the system would have the energy of 1.22 joules. Okay. And so this is just, again, to emphasize that that value function can be anything that we can associate with those probabilistic states. Now, there are some problems with empirical probabilities, we use descriptive statistics, and those are not predictive. If we have a large sample size, we can have a confident description of the system, but if the system changes and we don't know it, then we could be wrong, okay, in predicting the future. If nothing changes, if everything's going to continue behaving the same way, then we can have a confident decision-making process, but large sample sizes are expensive, and we can't always tell if the system has changed. So descriptive statistics show correlation. They show that two events show similar mathematical trends, but they don't show causation, that event one causes event two. That requires a different type of study. Okay. So descriptive statistics are not explanatory. What do I mean by that? Well, I might be able to show that high cholesterol correlates with heart disease, okay? But notice how that doesn't explain anything. It just says these two follow each other in terms of trend. The explanatory part is when I get into say, what is it about cholesterol that gets into the body that makes things happen? So, does it cause a plaque to form in the arteries? Okay, so then I now have an explanation. But just knowing that something's correlated with something else is not explanatory. You just have a hint that there might be a connection. And so to emphasize this, let's look at this. So correlation of two events does not mean that event one blank event two. So this is, again, I'm testing out the text feature here. One more. Okay. Very good. Yeah, causes is what I was looking for. These would be two different events. So I wanted to see if someone said that they saw a thing that said word cloud, show in word cloud, and I don't see that anywhere. Yeah. I was hoping that would be a possibility, but it's not. Okay. So just to emphasize that causation or correlation is not causation, this is one of my favorite websites, tylervegan.com. So you can write that down and go look at it later. Tyler, TYLERVIGEN.com. And he has dug through tons and tons of data just because he likes doing this apparently, to find what we call spurious correlations. So spurious means it's outwardly similar but falsely connected. And so here's the correlation of U.S. spending on space science and technology and suicides by hanging, strangulation, and suffocation. Mm-hmm. And it's correlated to 99.79%. Isn't that crazy? But are these really connected? Does one cause the other? No. We have no reason to think that there's any kind of connection to those things. Okay. Okay, what about this? Apple iPhone sales correlates with people who died by falling down the stairs. It's tempting, right? It's tempting to say, well, so this is where we could do it. What should be done, right? What should be done? And that's sort of you're just bombarded with this on the news constantly. They show a correlation, and that's the question: what should be done? Call your congressman. Let's get this fixed. When they haven't shown a connection, they've shown a correlation. So I'm just part of this. Since we're talking about probability, I'm passionate about sort of opening your eyes to what's going on around you, especially in terms of correlation and causation. So maybe nothing should be done. Maybe these things aren't connected at all, but they do correlate. But your question sometimes with these correlations to be, well, so what? I mean, they're correlated, but that's just a mathematical, similarity. This one's even funny. Works of visual art copyrighted in the U.S. Inversely correlates with females in New York who slipped or tripped to their death. So if we have more works of visual art, fewer females will die in New York. 93 or 94% correlated. Okay, so what should be done? We need more art in New York. Lives are at stake, right? And so it's just funny, and there's a bunch of others on there it's just so funny to go to that. So that's pretty much all I have. The main points today was just that when we get into energy levels and we throw molecules and atoms and electrons at them, it's really like musical chairs. They're going to find the first energy level available, and then as they come to thermal equilibrium, they'll match the Boltzmann distribution. So next time we're going to talk about the Boltzmann distribution. All right, I'll see you then.